Here is a stationary object. It's not broken down. We're using it in an experiment. To move it, we apply a force. In fact, let's go wild and apply two. It remains stationary because the forces balance out to zero. We're going to look more at resultant forces, and just to add to the excitement, let's look at terminal velocity too. Imagine that we hadn't banjaxed the car. Here is a force diagram. You can tell because it's got arrows. What do you notice about the arrows? Yes, apart from the fact that they're in different colours. Yes, and apart from the fact that they are pointing in opposite directions. They cancel each other out exactly. We say there is no resultant force, so our car doesn't start to move. The forces are balanced here too. The car isn't going to get faster or slow down. It's going to carry on at this steady speed. Thrilling. So whether a thing is stationary or moving, no resultant force means no change in velocity. Sometimes though, stationary things do start moving. I've seen it happen. The bigger the resultant force, the greater the acceleration. Right. The big one. If we apply the same force to both, what will happen? Correct! They had the same force, but more mass means less acceleration. We can join all this up in an equation. Here it is, and it's dead famous. F equals ma. F, the resultant force, equals the mass times the acceleration. F is measured in units called newtons, named after Isaac Newton, who came up with the equation in the first place. Mass is measured in kilograms, and acceleration is measured in, correct! Meters per second squared. Right, in your exam, you might be asked some questions. Let's calculate the acceleration of this truck. Its mass is 2,000 kilograms, and the force on it is 3,000 newtons. Force equals mass times acceleration. So do the maths, and the acceleration is 1.5 meters per second squared. Don't forget, there are lots of forces that can act on an object. Typical forces that you might come across in the exam are air resistance, friction, gravity, and one called contact force. Let's go through them all. Air resistance depends on the shape of the object and its speed. It's sometimes called drag, and it acts in the opposite direction to the motion. Car designers make cars more efficient by reducing the air resistance. But then people go and add roof racks and a roof box and fridges and mess it all up again. Contact force, what's that? It happens when two objects are pushed together. They exert equal and opposite forces on each other. Contact force is everywhere. In fact, even standing still, your weight is pushing down on the ground. You'd sink into it if there wasn't a contact force pushing back. This is the force you should feel in your feet. Now, friction is the force when things rub together. Friction works against the motion. Moving through a fluid causes friction too. The faster you move, the greater the friction. That's why swimming is hard work. Air is a fluid too, by the way. Gravity is the force that pulls objects towards the centre of the Earth. We call the force of gravity on an object its weight. The Earth pulls with a force of about 10 newtons on every kilogram of mass. A free-falling object accelerates at first, but this increase in speed increases the air resistance too, until eventually the downward force of gravity equals the upward drag. This means no resultant force, so that means no more acceleration. Remember, the object is now falling at a steady pace. We say that the object has achieved its terminal velocity. Have an achievement. Increase the drag and the terminal velocity will be less. Good, but better still to use a parachute. It's more traditional, and the air resistance will slow you down to a safe speed.